Okay, everyone, here we go with the first video lecture for chapter 17. There will probably be two video lectures for this chapter, I imagine. So chapter 17 is still concerning statistical inference, like we've been talking about for the past few chapters. But up until this point with statistical inference, we've been concerned with situations where we assume we know what the population mean and the population standard deviation is. In this chapter, we're going to introduce a new statistical tool for use in situations where we don't actually know what the population standard deviation is. Okay, and that's actually a much more realistic assumption to go on. In most cases, we don't know what the population standard deviation is, and so we have to have some way to deal with that in terms of using statistical inference analysis. Okay, all right. So basically in this chapter, we're going to be dealing with what's called the t-test. Okay, the t-test is the test for, or the statistical inference test that we use when we don't know what the population standard deviation is, when we don't know what sigma is. Okay, and the t-test is based on a different distribution than we've used before. It's based on what's called the t-distribution. So this is a little bit different than the sampling distribution that we used when we were calculating z-scores. Remember, because in those cases, we were operating under the assumption that we knew what the population mean was, and that we also, more importantly, knew what the population standard deviation was. All right, so let's move forward here. Okay, so basically, with regard to sampling, I've said before that the larger sample you can collect, the better off you're going to be in terms of your statistical analysis. And that's always going to be the case, okay? We talked about in the past how with larger sample sizes, your sampling distributions were more accurately going to reflect the population mean, okay? But now here with a situation where we don't know or where we're more concerned with the standard deviation of the population that we don't know, also the larger the sample, the better or more reliable estimates of the population standard deviation that we get from our sampling distribution. So with a small sample, you're not covering much of that overall level of variability. And so your idea of how wide the curve is, how wide the sampling distribution is, which again is based on standard deviation, is not that good. But when you have a larger sample, you cover much more of that overall variability. You can wrap your head around more of that variability, so to speak, get a better picture of it. And so your estimated sampling distribution provides a better estimate for the population standard deviation than if you had just a small sample. So again, this goes back to the central limit theorem that we talked about before. Okay, so let's talk about the t-distribution a little bit. All right, so I'm going to have to fill in a few things here with these formulas again, as usual. I'm not sure why the iPad does that. Anyway, the idea is that, with sampling, we always take one random sample of a certain size from, hopefully, we hope, a normally distributed population. And remember that population is described in this way, through this notation. So it's normally distributed, and you have a specific mean, or population mean, that's mu, and a specific population standard deviation. Remember, as long as you know the mean and the standard deviation, you can draw that curve, right? Okay. Well, in this case, we don't know what the population mean or the population standard deviation is. We don't know what these figures or values are. So we're going to infer them from our sample, which comes from that population. So remember that when we know what sigma is, when the population standard deviation is known, the sampling distribution of the sample mean is normal, okay? And it should have the same mean as the population, but it will have a standard deviation defined as the sampling standard deviation, as the population standard deviation divided by the square root of the sample size. Remember, that's going to be the standard deviation for our sampling distribution that this sample came from. Okay, and remember from that, we calculated a z-statistic, right, a z-score, which was the sample mean minus the population mean over the population standard deviation divided by the square root of n. And that follows a standard normal distribution. Okay. Now, when we're estimating the population standard deviation from our sample standard deviation, okay, we have to calculate the t-statistic or the test statistic. And it's very similar. It's, again, the sample mean minus the population mean over our sample standard deviation, that's S, divided by the square root of n. So remember, back in the beginning of the semester, we talked about the difference between parameters and statistics. Parameters define populations, such as the population mean, which is mu, or the population standard deviation, which is sigma. So we have Greek letters for those. But in samples, we have statistics that define characteristics of those samples. And those are usually, well, it's usually going to be the sample mean and the sample standard deviation, but they're English letters, described by English letters. So the sample mean is X bar, and the sample standard deviation is now S, all right? Okay, by the way, this denominator right here, the sample standard deviation divided by the square root of n, that is actually a new statistic called the standard error of the mean, or the SEM for short. We're going to see that more here in just a little bit, okay? All right. So again, when we are estimating population standard deviation from the sample standard deviation, we calculate a test statistic, t this time, and it follows what's called a t-distribution, okay? And it will have n minus 1 degrees of freedom. This is just a correction for the sample size. So sample size is n, subtract 1 from it, and that is what's called degrees of freedom. You're going to need that to be able to use the table to look up a t-value here in just a little bit. All right, so let's look at some distributions here. So here at the top, we have three different density curves or distributions, right? So the black curve is our standard normal, okay? That's what we've been doing with z-scores and all that, right? That's the standard normal curve for a sampling distribution that we've been looking at. Now, the blue curve is a t-distribution with a sample size of 2. So remember, degrees of freedom, in this case being 1, degrees of freedom is n minus 1. So your sample size must be 2. 2 minus 1 gives you degrees of freedom of 1. So notice that at small sample size, your curve is more narrow here, but there's more area in both tails. So it differs in its overall shape from the standard normal sampling distribution that we've been used to dealing with. But then look what happens as your sample size increases. So sample size of 5, which gives you degrees of freedom of 4, that's the red line. You see it's more closely approximating that standard normal curve. It's getting closer to it. Then look down here, degrees of freedom of 20, so sample size of 21. You can barely discern a difference between that blue line and the black line, right? Between the t-distribution for a sample size of 21 and standard normal. But then what about a sample size of 101, degrees of freedom of 100? Well, now it's pretty much spot on that standard normal curve. So again, this is central limit theorem, right? When the sample is large, the sample standard deviation is a good estimate of the population standard deviation. And that's what these curves here are showing you, okay? That is the point that this is trying to make. All right, it's an important one to remember. Okay, so now we're dealing with table C. Now we've dealt with table C before, actually, but up until this point, all we've done with table C is set a certain confidence level, usually 95%, and from that, we have found a z-score, right? Say 1.96, for example, as our z-score for 95% confidence. Remember, that's a measure of standard deviations away from the mean. We could also then use that to figure out p-values, right? That's all we've done so far with table C. But now we're going to start using these numbers in the body of the curve, and let me fill this in. These numbers again are test statistics, okay, t-statistics, or values of t, okay? So we're going to see how we use those here just in a little bit to do what's called a t-test. Now a t-test is a little bit different from a z-test, which we've done before. The t-test, again, is going to assume that we don't know, or operates under the assumption that we don't know what the population standard deviation is, and so instead we're using our sample standard deviation to estimate the population standard deviation. All right. So, moving on. Okay, so standard deviation versus something called standard error. Well, I mentioned standard error here just a minute ago. Let me fill this in. Oh, this is frustrating. All right. So remember that we had earlier in the semester talked about sample standard deviation, right? And this is the formula for it. Basically, you calculate your sample mean, you subtract that from each individual data point in your sample, square that difference, that gives you squared deviations, add them up, that gives you the sum of the squared deviations, then divide that by n minus 1 and take the square root. That gives you S, the sample standard deviation. It's just a measure of variability amongst the data points in your sample. All right, so we talked about, or mentioned, standard error of the mean here just a minute ago, right? If we take that standard deviation, the sample standard deviation, and divide it by the square root of the sample size, we get the standard error of the mean, or SEM. This is very commonly reported in scientific papers. They'll usually report the mean plus or minus the standard error of the mean rather than using the standard deviation, although sometimes standard deviation is used. It's just a different way to express variability, but importantly, it is the denominator in the calculation for the test statistic. That's why we're talking about it here, okay? Now, if you know what the standard error of the mean is, you can calculate or back calculate the standard deviation. So, look at the bottom. A medical study examined the effect of a new medication on the seated systolic blood pressure. The results were presented as mean plus or minus the standard error of the mean for 25 patients are 113.5 plus or minus 8.9. Question is, what is the standard deviation S of the sample data? Okay, well, you know that the standard deviation of the mean, the standard error of the mean is the standard deviation divided by the square root of n. So if you just reverse that, okay, and take take the standard error of the mean and multiply it by the square root of n, then you get your standard deviation back, and that's what they've done right here. It's just really showing you that there's a relationship between the standard deviation, which we've talked about a lot so far this semester, and now our new statistic, the standard error of the mean, okay? But the more important aspect of the standard error of the mean is not that. The more important aspect is that it's the denominator in our calculation for the test statistic, okay, the t-statistic. Okay, so what we're going to talk about here is called the one sample t-test. Sometimes you see this referred to as the student's t-test, but there are actually various different kinds of t-tests. There are about 3 of them, and this is the simplest one, the simplest case. So we're going to start with it, okay? So remember, whenever we're doing a hypothesis test for statistical inference, there are a number of steps we have to go through. First of all, we have to state our null hypothesis, okay? And that's always going to be a hypothesis about the population mean. We decide whether or not we have a one-sided or two-sided situation, or a one-sided or two-sided alternative hypothesis. We choose our significance level alpha. So remember, if you set your confidence level at 95%, which is most common, then you're dealing with an alpha of 5% or 0.05. That's your cutoff against which you evaluate the p-value you calculate. Lower than your alpha, you reject the null. Higher than the alpha, you accept the null. We're going to calculate our test statistic, t, and its degrees of freedom. We find the area under the curve with table C, or we can use software, okay? And then we state the p-value and we conclude. So this is a very objective step-by-step process. This is exactly what we would have done with a z-score in a situation where we knew what the population standard deviation is. Now we're just modifying it slightly under the assumption we don't know what the population standard deviation is, and that's why we're now using the t-distribution and calculating a t-test, or a test statistic for a t-test. Okay, so the idea is that we draw a random sample of a given size from a normally distributed population, right? And it has these characteristics, okay? When our population standard deviation is being estimated from our sample standard deviation, so we're estimating sigma from our sample standard deviation, the distribution of the test statistic, t, is called a t-distribution, and it has degrees of freedom of n minus 1. All right, so again, we need to define our hypotheses. So our null hypothesis is that our population mean equals our null mean. So mu0 is our hypothesized null mean, okay? The test statistic, again, is our sample mean minus our hypothesized mean over the sample standard deviation divided by the square root of n. All right, so this gives us a test statistic called t, and we're going to look at or use table C to figure out what p-value corresponds to whatever test statistic we calculate. All right, so t is just like z in the sense that it is a measure of standard deviations. It's going to tell us how far away from the mean, the hypothesized mean, that sample mean falls, and based on that, we're going to figure out what the likelihood is of getting a sample mean that far from the hypothesized mean if our null hypothesis is true. We then use that to determine whether or not to accept or reject that null hypothesis. So the resulting t-test that we get here is, as we say, robust to deviations from normality. That's true as long as we have a large enough sample size. So what this term robust means when you see it in a statistical sense, it means that the test you're talking about is not greatly affected by deviations from normality. It's not greatly affected by skew or outliers, that kind of thing. The t-test is a fairly robust test as statistical tests go. There are other tests that are less robust. They're much more affected by skew, non-normality, outliers, that kind of thing. But the t-test is pretty good. I mean, you got to have a certain sample size, but probably the lowest sample size of most tests that you would need to be able to use this particular type of test. Okay, just a refresher on the p-value. Again, the p-value is the probability, assuming that the null is true, of randomly drawing a sample like the one we have, or more extreme in the direction of the alternative. And again, that's just a fancy way of saying that the p-value is the probability of getting a sample mean as far from the null mean as we have if the null hypothesis is true. And the lower that probability, the more likely we are to reject the null and make the assumption that that sample mean is from a different population. Okay, but also remember, we have different kinds of means here, okay, or hypotheses rather. We have one-tailed versus two-tailed. Okay, so let me fill this in again. All right, so remember, for a one-sided test, we're dealing only with one tail or the other of our distribution. For a two-sided, we're dealing with both, which means the sample mean could fall in either one of those, right? So this is something we have to decide at the outset when we're designing our experiment. Is our question a one-sided alternative or is it a two-sided alternative? And the reason we have to figure this out is because it affects the calculation of the p-value. All right. So this is table C. Table C is a little bit busy. There's a lot going on, right? But whereas, as I said before, we had used this top row, the confidence level, to figure out basically a z-score down here, then a corresponding p-value. Now we're going to be using these numbers in the middle. These are values of t, okay? So test statistics. All right. So let's say that we have an alternative hypothesis that our population mean is greater than our null mean, our null hypothesized mean. Sample size equals 10, and we have a calculated test statistic of 2.7. That means that whatever the sample mean is here, it lies 2.7 standard deviations away from our hypothesized null mean. Well, you should know already, based on the empirical rule, that because that's more than 2 standard deviations away, we're probably better than 95% certain that that sample mean is not from this population. It's too far away from that hypothesized mean. So in this case, we're going to reject that null hypothesis. But let's look at the p-value to find out if that's true or not. Okay, so we have a test statistic of 2.7. We have a sample size of 10. So notice that we have a degrees of freedom column here. We have to find the appropriate row of the table, and that row is the appropriate degrees of freedom for our sample size. So degrees of freedom is n-1. We have an n of 10, so degrees of freedom is 9. Right there, that's what we're looking at. So we have to look on this row, And we have to find where 2.7 falls. Not here, not here. Right there. It falls in between these two test statistics. So follow table down. We have a one-sided test. Our p-value should be between 0.01 and 0.02. Okay. All right. So again, t of 2.7 lies between these two critical values on our table. So our p-value is between 0.01 and 0.02. All right. And you can see that 2.7 falls way over here. This little sliver of area to the right of that is less than 5%. It's probably more like 0.5%, 1%, something like that. It's hard to tell, but the p-value basically tells you, okay, what that percentage is, what that area is. Remember, p-values are probabilities, so they're areas on our curve. Okay, let's look at an example here. So, study participants, there were 53 obese children aged 9 to 12 with a body mass index above the 95th percentile for age and gender. This means that 95% of other children in the same age group have body mass indexes lower than these children. Okay, so they're fairly overweight. All right, they were put on an intervention plan, which included family counseling sessions on something called the stoplight diet, and after 8 weekly sessions and 3 follow-up sessions. The assessment was the change in weight at 15 weeks of intervention. Okay, so they're just looking to see if they gained weight or lost weight based on their initial weight measurements before they started this intervention program. Question is, was the intervention effective in helping obese children to lose weight? So because we're assuming that this intervention program is designed to cause weight loss and not either weight loss or weight gain, we can assume this is a one-sided test. All right, so our null hypothesis is that our population mean is 0. So what does that mean? The population mean weight change. Okay, so if this is not effective at all, there should be no change in weight over that 15-week period, versus the alternative that it is actually an effective weight loss program, and so we should see a weight loss of less than 0. That means, a weight change of less than 0. If you have negative weight change, what do you have? Weight loss. So look at the raw data over here for these 53 children. You see one lost 16.7 pounds, one 14.8, and so on down the line. This one lost none, and these actually gained a little bit of weight. So if you plot these out on a dot plot, you can see that the null mean is 0 right there, and more points do seem to fall to the left of it. We had a mean weight loss of minus 2.4 pounds, so that falls somewhere right in here, and so it's to the left of that. The question is, though, is that difference between our null mean and our actual sample mean, is that due to this stoplight diet and intervention program, or is it just random variation? That's always the question we're asking when we do a test of statistical inference, okay? All right, so we have, this is a printout from like Minitab. We have sample size of 53, a mean weight change of minus 2.4 pounds. This is the standard error of the mean. So again, that's the standard deviation divided by the square root of n, and this is our standard deviation. All right, so if you take the standard deviation and divide it by the square root of 53, you get this, 0.72. That's standard error of the mean. That is the numerator in our calculation for t. All right, so let's take a look at the results. Okay, so here's our Minitab output. So we have a test of a null hypothesis that there's no weight change versus an alternative of a negative weight change, weight loss. Sample size 53. We have a mean of minus 2.4, standard deviation 5.243, standard error of the mean 0.72. So you work that out, and here's the formula again for doing so. You get minus 3.34 as your value of t. So we have our sample mean of minus 2.4 minus our hypothesized mean of no weight change, 0, over our sample standard deviation divided by the square root of n. That's our standard error of the mean, 0.72 from the table above. Work out the math, you get minus 3.34 as your test statistic. And again, that test statistic is a measure of standard deviations. So think about your empirical rule. We want to be 95% certain, right? That would mean the t-statistic would need to be right around about 2 standard deviations. Well, this is 3.34 standard deviations below that null mean of 0. So it is way far over to the left, and you can see that right there. That's the printout from a calculator, it looks like. So let's go and find this value on our table to see what the p-value is, okay? Well, one thing about the table, degrees of freedom, is that once you get up to like 30 or 40 or something, the numbers start to go by tens, and then even higher after that, right, as you go this way. So we don't have a 52 degrees of freedom. Again, n minus 1, 53 minus 1, 52. There isn't a 52 degrees of freedom row, so when that's the case, you go to the next lower value. So you would go 50. All right, so follow this all the way over. We're looking for minus 3.34, and we see it falls between these two values, okay, right at the end of the row. Go down, and we have a one-sided p of between 0.0005 and 0.001. All right, Minitab calculates it much more precisely and says 0.0008, which, yes, is the in-between these two numbers. All right, so that is statistically highly significant, okay? And you know that because the t-value came out to be more than 2, which would be about 95% confident. That would be right at your 0.05 cutoff. This is well beyond that, way over here to the left-hand side of that curve. So we know it's significant. We need the table, though, to tell us just how significant. And that is just how significant right there, okay? All right. Now let's talk about confidence intervals. So we've talked about confidence intervals already in this course. And remember that a confidence interval is nothing more than a range of values along our x-axis of whatever we're measuring in our sample that contains the true population parameter, usually the mean, with a given probability. So if you set your confidence level at 95% and you calculate a 95% confidence interval, then you are 95% confident that your true population mean lies within that interval, okay? You're not absolutely certain, you're 95% confident, but typically that's what we use. So we have a set of data from a population with both our population mean and our population standard deviation unknown. We're going to use a sample mean to estimate the population mean and our sample standard deviation to estimate the population standard deviation. We have a t-distribution defined by degrees of freedom of n minus 1. All right, so again, see here, this area between these two values shaded in yellow, that's our confidence level, right? So we have a confidence interval here, and it is defined as some area on this curve, okay? All right, remember also that the confidence interval is twice your margin of error. So we have to be able to calculate margin of error. And we did this for z-scores in the previous chapter or two. Here it's no different. Previously, we said the margin of error was our z-score multiplied by the population standard deviation over the square root of n. Well, we don't know what the population standard deviation is here. So we're going to use, instead of z, a test statistic, t. And instead of the population standard deviation, we're going to use our sample standard deviation. So our margin of error then is a t-score times our sample standard deviation over the square root of n. That will give us 1/2 of our confidence interval. That's what a margin of error is, okay? All right, let's look at an example. So data on blood cholesterol levels in milligrams per deciliter of 24 lab rats gives a sample mean of 85 and a standard deviation of 12. We want a 95% confidence interval for the mean blood cholesterol of all lab rats. All lab rats. That means the population. So we're trying to estimate for the population based on the sample from that population. Okay, so 24 lab rats, mean of 85 and a standard deviation of 12 at a 95% confidence interval. So we go back to our table, table C, and we see a degrees of freedom of 23. Remember, n minus 1, 23. At 95% confidence, we have a t-statistic of 2.069, all right? Okay, so our margin of error then is our t-statistic times, that's not decimal, that's times our sample standard deviation over the square root of n. So plug in your t from the table, 2.069, and multiply that by standard deviation of 12 over the square root of 24. Our sample size, work out all the math, we get a margin of error of 5.07. All right, this is not a t-statistic. We used our t-statistic to calculate this, which is the margin of error. So our sample mean of 85 plus or minus our margin of error of 5.1 gives us a confidence interval of 79.9 to 90.1. So 85 minus 5.1 is 79.9. 85 plus 5.1 is 90.1. So that is our margin of our confidence interval, 95% confidence interval. Okay. So this means we're 95% confident that the true mean blood cholesterol of all lab rats, the population, is between 79.9 and 90.1 milligrams per deciliter. And we came to that estimate based on a sample of 24 lab rats. All right. Okay, well, I think that's a good place to stop for this first t-test. This was a one sample t-test where you're taking a single sample mean and comparing it to some hypothesized mean. At the beginning of the next video lecture, the second part of this, we're going to talk about another kind of t-test called a matched pairs t-test. It's a little bit different, but it's based on the same basic principle. All right, so we'll pick up with that.